Welcome to Consumer Theory. Every day, a Macola market trader or a Cross civil servant solves the same problem, allocating a limited budget across competing wants. Our goal is to translate that messy, subjective human desire into rigorous mathematics. Before we can model choice, we have to define exactly what a consumer is choosing among. We map this universe of possible choices as a consumption bundle, a list of quantities for every available good. These bundles live inside a mathematical space called the consumption set. This visualization models the standard continuous consumption set. Notice three specific properties. First, it is bounded below by zero. You cannot consume a negative amount of a good. Second, it is closed, meaning it contains its own boundary. And third, it is convex. Mixtures of feasible bundles are also mathematically feasible. The mathematics rely on a continuous approximation, which assumes goods are perfectly divisible. Real-world items like a Trotro or a refrigerator are indivisible. While we acknowledge discrete items, standard theory relies on the continuous space to keep calculus well-behaved. Consider the self-check from the module, a rural farmer allocating her output between cocoa sold to CocoBod and plantain kept for the household. Think about her consumption bundle notation. Are her options truly a continuous, non-negative orthant? Within this set, a consumer ranks bundles using specific notation. Strict preference means one bundle is strictly better. Weak preference means it is at least as good. Indifference means both bundles provide the exact same satisfaction. Defining this topological consumption space is the mandatory first step. We must map physical feasibility before introducing market prices, budgets, or optimal decisions. For these rankings to be useful, they must follow rules, which we call axioms. The first is completeness. A rational consumer can always compare any two bundles. They prefer A to B, B to A, or they are indifferent. There is no unresolved indecision. The second axiom is transitivity. If a consumer prefers bundle A to bundle B and prefers B to C, they must prefer A to C. Their preferences must possess strict internal consistency. This animation illustrates transitivity failing. Imagine a student who prefers Jollof to Woki, Woki to Banku, but also prefers Banku to Jollof. This creates a preference cycle. An observer could exploit this indecision through a money pump, charging the student a fee to constantly trade meals in an endless loop, draining their budget while leaving them exactly where they started. This is why we rule out cycles. In your study module, look at Self-Check 1.2. Try using formal notation to prove that if strict preference is transitive, indifference must be transitive as well. Without completeness and transitivity, preference relations fail to form a coherent ordering. This logical breakdown prevents us from applying calculus or deriving demand functions altogether. Next, we assume local non-satiation, or strong monotonicity. Holding all other consumption fixed, more of any good is strictly better. A higher mobile money balance is always preferred because you can simply choose not to spend it. The consumer is never fully satiated. We also assume convexity, which formalizes a preference for diversification. Mixtures of two equally good bundles are at least as good as the extremes. A balanced plate of rice and protein is preferred to an extreme diet of only one or the other. This graph illustrates lexicographic preferences, the ultimate test of our final axiom, continuity. Here, goods are ranked like words in a dictionary. Good 1 is decisive, and good 2 only breaks ties. Watch what happens when we try to plot the preferred 2 set for the bundle 1, 0. Any bundle with more of good 1 is preferred, regardless of good 2. But exactly at x1 equals 1, the limit point behaves strangely. No finite amount of good 2 can ever compensate for the smallest reduction in good 1. There is no room for a continuous trade-off. The preferred 2 set has a gap. It is not closed. Because these sets are open and lack continuity, lexicographic preferences cannot be represented by any numerical utility function. They exhibit sudden mathematical jumps. Completeness, transitivity, and continuity are the strict topological prerequisites required for calculus to function. Without them, consumer choice cannot be modeled. Look at this preference map. When completeness, transitivity, and continuity hold, de Bro's theorem guarantees that a continuous utility function exists to represent these preferences.
To construct it, we project a 45-degree ray from the origin, ensuring it intersects every indifference curve. Utility is simply the distance measured along this ray.
It tells you how far out you must travel, consuming equal amounts of every good, to be exactly as satisfied as you are with a given bundle. It is an ordinal distance mapping, not an absolute measure of human happiness. Because it is ordinal, utility is unique up to any strictly increasing monotonic transformation. A function like uxy equals xy represents the exact same preference ordering as xy squared. But a transformation like xy fails this test because it reverses the ordering of the outputs. By totally differentiating the utility function along a constant indifference curve, we derive the marginal rate of substitution. The MRS is the exact rate at which a consumer is willing to trade one good for another, and mathematically, it is simply the ratio of their marginal utilities. The specific numerical value of a utility function is entirely irrelevant. Only the shape, the order of the curves, and the resulting marginal rate of substitution actually matter for economic analysis. The consumer has desires, but they also face market constraints. Given strictly positive prices and a finite income, the consumer operates within a budget set, a closed, compact, and convex feasible region of affordable bundles. This animation frames the primal problem, or utility maximization problem. The consumer seeks the highest indifference curve that touches their budget set, expanding outward until achieving a perfect point of tangency. To find this tangency mathematically, we set up a Lagrangian equation. We combine the objective function, the utility we want to maximize, with the budget constraint, linked by the Lagrange multiplier lambda. Taking the partial derivatives with respect to x1, x2, and lambda gives us a system of first-order conditions. By dividing the first two conditions, the lambdas cancel out, revealing the core tangency condition. The ratio of marginal utilities equals the ratio of market prices. Tangency is the exact mathematical moment where a consumer's highly subjective internal desires align perfectly with the objective reality of market prices. At this point, the rate they are willing to trade equals the rate the market forces them to trade. Solving those first-order conditions yields the Marshallian demand function. This function maps directly from given market prices and consumer income to the optimal consumption quantities of each good. Marshallian demand obeys Walras's law, meaning the consumer exhausts their entire budget. It is also homogeneous of degree 0. If you double prices and double income simultaneously, the optimal choice remains exactly the same. If we plug these optimal price-dependent quantities back into the original utility function, we derive the indirect utility function. It tells us the maximum utility achievable at any given set of prices and income. From here, we can use Roy's identity. It serves as a mathematical shortcut, allowing us to extract Marshallian demand functions directly from the indirect utility function using simple partial derivatives, bypassing the need to resolve the entire Lagrangian. Optimal choice is a predictable, differentiable function, linking macroscopic market forces directly to human satisfaction. There is another way to look at this same tangency point. In optimization theory, every primal problem has a dual problem. For the consumer, this is the expenditure minimization problem. Watch how this inverses our approach. Instead of maximizing utility within a fixed budget, we lock a target utility level in space. The objective is now to minimize expenditure, pushing parallel budget lines inward from infinity until they just barely touch the required utility floor. Solving this dual problem yields the Hicksian demand function, alongside the expenditure function, which dictates minimum cost for target utility. Shepard's lemma provides a shortcut. Differentiating the expenditure function by price instantly yields Hicksian demand. The utility maximization problem and the expenditure minimization problem yield the exact same optimal bundle. Every maximization problem in economics hides a minimization problem inside it, containing the exact same behavioral truth. The Slutsky equation links Marshallian and Hicksian demand, providing the calculus to deconstruct exactly how consumers react when a price changes. We begin with initial optimal bundle, A. When good one's price drops, the budget line swings outward, moving the consumer to a new optimal bundle, B. This total effect hides two conflicting psychological forces.
First, look at this pivot along the curve, isolating the substitution effect. The changing price ratio means substituting away from expensive goods toward cheaper ones. Second, the price drop expands purchasing power, creating a parallel shift that isolates the income effect. The Slutsky equation adds these together. The substitution effect is negative, but the income effect dictates the final outcome, defining a normal, inferior, or Giffen good. This completes the self-study module. Before the live block session, review your derivations for the Slutsky equation and the Lagrangian setups. Bring your unresolved questions, specifically around boundary corner solutions, directly to class. Aggregate market reactions, including the counterintuitive rise of a Giffen good, are the visible result of millions of individuals balancing these hidden pivot and shift decisions.